Welcome to this another video on the power quality. In this video, we'll have a discussion on that two-wire passive compensator. And in the first video, this is the second video of that two-wire passive compensator. And here in this video, we will focus on that power factor correction at the substation. That means we will focus on that Vs and Is that can be equalized. Right, so just let us have some quick glimpse of that circuit diagram. So again, let me just again say about this parameters. We have here Rs and Ls. These represent the resistance and inductance of the transmission line. And here we have the supply voltage Vs and Is is the supply voltage and supply current. And the load is represented by the admittance. So admittance multiplied with the voltage give you the current. Rather than we have the impedance multiplied with the current, as we know that the Z can be written as R plus JXL, which is usually the inductive in nature. So if we write 1 by Z, this is nothing but Y, and that we can write in terms of minus J by like this, and J by R square plus XL square, and XL by R square plus XL square. We can just solve that we have discussed in the first video of this two-wire passive compensator. And now here our objective is to draw the phasor diagram so that the Vs and Is, these two, get equalized. So here is a phasor diagram. Let me put both this picture and this in the same figure. So here we have that VL and multiply with the GL. There is no J term. So this VL and GL is in the same direction of the VL. Let us say VL is the reference. Again we have the VL multiplied with the BL with a minus of J term. So minus J term means it will be downward, obviously, negative y-axis. And if we add these two, VL and admittance Y, so it will give to the value of IL. So the value of IL will be in this direction because the phasor sum of these two values, so we get the value of IL. Again, because the VL is the reference, we have taken this VL is also multiplied with the JBC, that is the compensator that we add. So this J is like positive y-axis, so we get the positive y-axis in the upward direction, and that we get the value of IC. Now this value of IC, it's in our hand, the BC value we choose. So what we need to do is IL and IC, the phasor sum of these two will be IS. So like we have to a little bit give of IC value so that these two will have a phasor sum of these two like this. We have resultant is the IC, which is the phasor sum of these two, and we get the IS value in phase with the VS. If I compare with the power factor correction at the substation and the power factor correction at the load terminal, what's the difference is that here we need a value of IC a little bit of more, like this much is a little bit more value, whereas here we require less, because here the resultant IS is here. Resultant IS is here, however here the resultant IS is a little bit upward. So we need a higher value of IC to keep the power factor at the substation unity. So if the IS direction is here, so obviously when we multiply, like using a KVL, VL we add with the IS into RS and IS into JXL. So we have a VL, and this IS into RS is getting added with the VL. So if we add this, suppose the VL is over here, and we add this value of IS into RS, which is in parallel with IS over here. So IS plus RS will be, once again, this is VL, IS RS will be here, and then we can add this impedance. Then we can get the value of VS. Either we can do in this way, that is we are adding this VL, IS into RS and IS into JXL by KVL. We just add these three and we get the value of VS. Or else we can do that Vs minus of this, and we get the value of VL. So if the Vs is like this, you subtract the value of ISRS and then subtract the value of J is excess, and what we get is we get the value of VL from like this. So this is the power factor correction at the substation end. In another video we'll see that a two-wire passive compensator, if the voltage regulation is done, then what could be the power factor correction.